The next type of graph we're going to look at are what are known as velocity time graphs. A little bit different than a position time graph in that it describes the object's velocity over a given amount of time. So just to show you real quick recap, I've drawn two graphs here, a position time graph and a velocity time graph. Now I've made the actual graph itself similar. You'll notice the only difference between these two is the fact that the y-axis here measures velocity in meters per second, whereas for position time graph, it measures the position of the object in meters. Outside of that, everything looks identical, and that's one of the reasons why velocity time graphs are sometimes easily confused with the position time graph. The important thing to realize is that because the y-axis is different, you're being given different information. So what concepts apply to one graph don't necessarily apply to the other graph and vice versa. The one thing that's nice is no matter what graph you're looking at, all graphs that you analyze, the slope will have some kind of meaning. So we know at this point for a position time graph that the slope will give me the velocity. So the slope of this line will be the change in the position or the displacement over the time, the rise y over the run x. So the displacement over the time. So that's why I get that slope is equal to the velocity of the object. So we'll do the same thing for a position time graph. However, to calculate the slope, we'll look at 2 points. It's still the rise over the run. However, in this case, the rise is actually the change in velocity, right? You had one velocity here, a certain amount of time later, you had another velocity. So you have a change in velocity over a given amount of time, rise over run. So if we take a look, hopefully it's not too much of a stretch to realize that the slope of a velocity time graph, because it's the change in the y, which is the change in velocity, over the change in x, which is the change in time, well, the change in velocity is just the change in velocity over time is how you calculate acceleration. So the slope of a velocity time graph will actually give you the acceleration of the object. So if we're looking at these two graphs, you start to realize that the slope of a position time graph will give you information pertaining to the velocity. The slope of a velocity time graph will give you information pertaining to the acceleration. So if we want to kind of go from one graph to the next, moving up from displacement to velocity to acceleration, we're just going to keep looking at the slopes in either one of those cases. So in every graph, the slope has some meaning, but hopefully you see that the slope for a position time is velocity, the slope for a velocity time is acceleration. So again, this is where these graphs tend to differ a little bit. So just to show you again why they can be easily confused, and then I'll go into a little bit more information about what we can derive from a velocity time graph, are two graphs we have here, a position time graph and a velocity time. And what we're going to take a look at is what's going on here. It looks identical, but it's really important that the y-axis is different. So if you take a look, the position is changing at a constant rate, and then the position is not changing. So this object is moving at a constant velocity because of the slope, and then does not have a velocity because it has no slope. Similarly, even though it looks similar over here, this graph is actually showing me that the velocity is actually changing, but changing at a constant rate. So while over here I had a constant velocity, even though the line looks the same, well, this is actually measuring velocity. I have a changing velocity. That's known as acceleration. Here I have no slope, meaning no acceleration, but the object is still moving because it has some positive velocity. For a velocity time graph, the object is only not moving when the velocity is zero, or the y value is zero. So it's important to realize that despite the fact that the graphs look the same, these are depicting two different events. An object travels with a constant velocity and then stops, and an object accelerates from rest but then continues to travel at a constant velocity. So hopefully you can see maybe here how these graphs can be easily confused, but if you keep track of which concepts apply to which, hopefully everything should be clear in the long run. The only other thing about a velocity time graph, well, we know that the slope equals the acceleration, but there's this other concept which is called the area under the curve. So first of all, what do I mean by that? Well, if you look at the x-axis and you look at the line that your graph is generating, there's some amount of space in between down here that's actually trapped. So the area under the curve is the area from the curve down to the x-axis. If this red line went below, it would be the same concept, but it would be from your line up to the x-axis. It's always the space entrapped by the x-axis and whatever your line is. This is more of like a trapezoid type shape, if I assume that this was closed off over here. But I can fairly easily just break that down into a triangle and then a rectangle. So just to show you how I calculate the area, I assume this was a triangle with a base of 2. 2 seconds, and a height of positive 4 meters per second. This rectangle had a base of 6 from 2 to 8 seconds and a velocity of positive 4 meters per second. So I've just kind of moved them over here. I have this triangle and I have this rectangle. To calculate the area of a triangle, it's 1/2 base times height. And to calculate the area of a rectangle or a square, it's base times height. So if you can see here that all I've done is break down the area that's entrapped by this graph into two shapes that I can more easily calculate the area of, I can just do that. 1/2 the base, which is 2 seconds, times the height, positive 4 meters per second. Well, the seconds will cancel out because I have seconds on the top and the bottom, and I wind up with positive 4 meters. If I find the area of the rectangle, 6 seconds times positive 4 meters per second, seconds cancel out, I get positive 24 meters, for a total of 28 meters in the positive direction. Hopefully that's screaming out to you, well, it's a distance or a length measured in meters, and there's a direction. What does the area under a velocity time graph give you? Well, it actually gives you the displacement of the object. So just to give you a quick recap, for position time graphs, the slope will give you information about the velocity of the object. For velocity time graphs, which is this newer concept, the slope will give you the acceleration, and the area that's trapped between your line and the x-axis will actually be the displacement that that object experienced. I have a nice little kind of, I don't know what to call it, a little chart that actually kind of cleans this up, I think, and it makes it easy to remember. If you can get used to drawing this, yeah, it should help things out. So delta x is displacement, velocity, right underneath that, and then the acceleration. So it's just the three topics we've spoken about: displacement, velocity, acceleration. Then going in a counterclockwise direction, I draw an arrow from the displacement to the velocity. I draw another arrow from the velocity to the acceleration. On the right side, I do the reverse. I go up from acceleration to velocity and up from velocity to displacement. If you can remember how to draw this little kind of pictogram and you realize that you write slope on the left and area on the right, it's fairly easy to understand. If I have a displacement time graph or a position time graph that shows me displacement and I would like to get the velocity, I calculate the slope. So the slope of this graph, position time, will give me velocity. If I have a velocity time graph, I have that velocity information, and I want the acceleration, well, I use the slope. If instead, let's say I have a velocity time graph and I want the displacement, I'm going to look at the area underneath this graph. We have not even begun to speak about acceleration time graphs, but hopefully you can see that if I did give you one right now and said, please give me information about the object's velocity, well, based on this little pictogram, you are going to calculate the area under that graph. So this will become a very, very hopefully easy to use and easy to understand tool, but it's just keeping track of what exactly the slopes and the slopes and the areas for each of these types of graphs represent. So it's a nice little way to remember it. If you can get used to drawing that and if you remember how it's drawn, should save you a lot of time. All right, lastly, I have an example here. So I'm just going to leave this up. I'll show you what I'd like you to find in a second, and then you can kind of jump back and forth to figure this out. But you have given a velocity time graph of an object that moves for a total of 11 seconds. Based on this graph, there's 5 things I'd like you to find. The first being the acceleration during the first 2 seconds. The second being the total displacement for the first 3 seconds. Then the acceleration from 8 to 11 seconds. What's the velocity at exactly 8.5 seconds into the motion? And then the total displacement for the entire trip. So I suggest you kind of pause this and copy down the chart. You can then copy down these answers. I'm not going to go through and read everything. I'm going to let you work through this. At the end of this, once you have everything written down and you've solved it, you can unpause the video. I suggest you pause it after you've done so. And then I'll scroll down and I will have the solutions posted so you can double check your answers before moving on to the practice work. So good luck.